All right. So, how's everybody doing? Okay. Good. So we had finished up our Feynman rules for QED. And we spent the first part of last time trying to justify those rules. And so here's our Feynman rules for QED. What's not shown here are, let's see, everything's shown here is the fermion property. That stays the same as in the case of the Buchanan theory. Okay, so we justified these last time, and we probably won't get a chance to prove them this semester, but if you want to read it on your own, chapter 8 or 9-ish. Hey, Brownsville, can you guys turn your mic down just a little bit? You know, the only problem is I can't see you guys today, so make sure you unmute it if you want to ask a question. Okay, so we had finally started to look at some real physics, right? And what we were going to look at was one of the simplest processes that you can look at QED, which is E plus E minus, goes to two muons, one positively charged, one negatively charged. And we've got all the formula we need. We've got rules to compute the matrix elements squared, so we're ready to start doing some real physics. In particular, we want to, like I said, we want to focus on this process. It's the simplest, but it might be the most important QED process because it allows experimentalists, especially working at E plus E minus colliders, to basically calibrate their machines, right? So it's a very well-known and very precisely known process as far as the cross-section goes and the distributions go. And so that allows experimentalists to calibrate their machine. Right? So we started to look at E plus E minus goes to V plus V minus. Like I said, Feynman rules, I always write time going from left to right. Okay, so this is E plus E minus goes to mu plus mu minus, right? And we applied our Feynman rules. So here's the fermion, the electron line. Here's the muon line. Here's the propagator for the photon. Right? And when I contract the G nu, I get two terms that look like this. Okay, and so what we need is this is one part of it. The other part is we need the complex conjugate of the matrix element. Right, and so we worked out how you work those out. Right? And we ended up with things that look like this. Right, so you just flip flop basically the order of everything, and in this case, a V became a V bar, and the U bar became a U. Okay. So we had gotten to this point, right, where we had put everything together. Compute the matrix element squared. We had basically two terms, right? This string coming from the electron line and this string coming from the fermion line. Right, and we said that most of the time we're not going to specify a particular spin state, either for the initial states or the final state particles. So what we do is we average over the initial state spins and sum over the final state spins. And so what we want to compute is something like this, right? So we're averaging over the two electron spins, S and S prime, or the electron and the positron spins. And the muons we're summing over, okay? And in that case, what we really need are these spin sums that we worked out towards the beginning of the semester. And those were going to come in very handy, right? So we wanted to put all that stuff together. And in order to do that, we had to do some reshuffling, right? So the way we did that was took one of these strings and explicitly wrote out the spinor indices, and that allows me to move this V to the front of the line, right? So I have V bar, and then U bar. And those I can take the spin sums of just by bringing them in sums. Those will give me these factors of P slash plus or minus M, right? And then when I look at the same person interrupted me. Good. What was I going to say? Right, so we're left with, so what we noticed was that the way the indices line up, it's given us the trace. Okay, so we have, from the electron line, we have this trace, and from the muon line, we have this trace. Okay, so we put it all together, and we ended up with something like this. All right, and this is a nice result because we've reduced everything to where there's no user V's around, so we don't have to deal with these 4-component spinners. And we have nice little compact expressions in terms of everything's in terms of gamma matrices, basically. Right? We just have to learn, we just have to figure out how to do these traces. Right? And it turns out that any QED amplitude or any time you're computing a process that involves fermions, you're going to have these traces, okay, when you compute the matrix element squared. Okay, and so what we want to do today is to develop the technology to be able to do that. Okay, so like we said, the traces of the type that we have, we're going to encounter, and they're going to pop up all over QED in any theory involving fermions. Okay, and they can be computed by what I call brute force. So that means plugging in the explicit expressions for the matrices themselves, right? And multiplying out the matrices and all that stuff. And nowadays it wouldn't be that big of a deal. You could write code, computer code or mathematical code or something that could do this for you, right? And in fact, there's packages out there. But back when Feynman was developing QED, he didn't have that at his disposal, right? But not surprisingly, he found an easier way to compute these things than doing the matrix multiplication by hand, right? And his method makes use of the algebraic properties of the gamma matrices. In other words, using their commutation or anti-commutation relations. Okay. Yeah. Okay. So what we want to do, our goal is to compute traces of n gamma matrices. Okay, so in our case, we have, when we look at this, right, we're going to have to take the trace of 1, 2, 3, 4, or 2, or there's cases where, I guess it's at 2 or 4, right? Yeah. But there can be in more complicated processes, there's going to be times where we're going to have to take the trace of up to 6 gamma matrices, okay? So what we want to do is try to develop a formalism or kind of just an easy way that we can compute these things and just write them down and and put them in the back of the book so we can flip to it anytime we run into these. Okay. All right. So that's what we want to do. Okay. So we're going to start with n equals 0 and work our way up. All right. So the n equals 0 just means I'm taking the trace of the identity. Okay, and that one's easy. So the trace of the identity is just 4 in this case. Okay. The trace, so the n equals 1 case is also easy, right? Because we've shown, and we've known for a long time that the gamma matrices are traceless. Okay? So the trace of one gamma matrix is 0. So those are, I mean, it's explicit here, right? But let's try to prove it in a slightly more general way, and it's going to help us build up the way we're going to try to compute these higher n values, okay? So let me take the trace of gamma mu, right? So I have the trace of gamma mu. I'm going to use the fact that gamma 5 squared is the identity operator. So I'm going to insert an identity operator in terms of gamma 5 squared, okay? And then I'm going to use the fact that gamma 5 and gamma mu anti-commute. Okay, so I'll pass one of these this gamma 5 through, and it gives me a minus sign. Okay, so that's using the anti-commutation relation. Right, and then I can pull the minus sign out in front of the trace. Right, so it's an overall minus sign. And then I use the cyclic property of the trace. Right, the cyclic property of the trace that tells me that I can pull this gamma 5 up to the front of the row, right, to where I end up with gamma 5 squared again, times gamma mu. Right, and then gamma 5 squared is just the identity operator. And so I get that the trace of gamma mu is equal to the negative of the trace of gamma mu. Right? And the only way that can happen is if the trace of gamma mu is equal to 0. Okay? All right, so that's a little more general way of showing it than working, because remember, this isn't some specific representation, the file representation. So we can use the same trick to take the trace of n gamma matrices. Okay? So what we would find, okay, when we do this is that when we try to take the trace of n gamma matrices, and we use this trick where we insert gamma 5 squared and then pass gamma 5 one of the gamma 5s all the way to the right, then we're going to pick up n factors of minus 1. Okay? We're moving this gamma 5 all the way to the right? So passing it through the n gamma matrices. Okay. So what that means is every time we do this, we're going to end up with this type of relation where, trace of n numbers of gamma matrices is equal to minus trace of n numbers of gamma, of odd numbers of matrices. So that means that the trace must vanish for n equals odd. Okay, so that's great, right? Because that cuts out half of our half of the numbers of gamma matrices that we're going to have to compute. Okay, all right. So what we need to do is focus on the even cases. Okay. All right. So let's look at the case for n equals 2. Okay. All right. And so what I want to do in order to compute this thing is I'm going to use the anti-commutation relation of gamma mu and gamma nu. So using the anti-commutator, I know that this thing is 2 times the metric tensor times the identity matrix. Remember, there's always kind of hidden in the commutation relations, there's a identity matrix there. And minus gamma nu, gamma mu, so with the 2 flip-flop. Okay? So I can take the trace of this term because I know that this is just a number, g mu nu is just a number. And this thing is, the trace of this is just 4. So I get 8 g mu nu. Right? And now I have the trace of gamma nu, gamma mu. Okay? But now I can use the cyclic property again. Right? So I can use the cyclic property to move gamma mu to the front. Right? And that's exactly what I have on the left-hand side. So I can move that over to the right-hand side and divide by 2. And I find that the trace of 2 gamma matrices, gamma mu and gamma nu, gives me 4 times the metric tensor. Okay? All right. So it turns out that the trace of any even number of gammas, right, because the n equals I case always gives us 0, can be computed in the same way. Okay, so the idea is that you have some trace of an even number of gamma matrices, right? And what you want to do is anti-commute the first one, all the way to the right. Okay, so you anti-commute it through, however many gamma matrices you have until you get to the end, right? And then at the end, once you've hit the far right, you use the cyclic property to move it to the front of the line. Okay.
It cannot are matrices, but G mu mu is just a number.
Yeah, so it's a number of times identity matrices there.
Oh.
Oh, no, it's a number. It's a number, right? Because, this would be a number. Right? So this is just a number, yeah. Yeah, sorry. Okay, so let me walk you through the n equals 4 case. All right, so let me start here. So I have the trace of gamma mu, nu, rho, sigma. Okay, I'm going to do the same thing I did before. So I'm going to take this guy, anti-commute it through the gamma nu. Okay, so it's going to give me a 2 times g mu nu piece times the identity matrix minus a gamma nu gamma mu. Okay, so here I've got the trace of g mu nu, which is just the number, times the trace of 2 gamma matrices. We've already worked that one out. Okay, so that term I don't have to worry anymore about. I just want to focus on this term. Okay, so now I'm going to take the gamma mu and pass it through the gamma rho. Right? So I use the anti-commutation relation. So it gives me this 2 g mu rho times gamma nu gamma sigma. Yeah, because I get gamma nu gamma sigma. Okay, and then the second term from that, moving that, gives me gamma nu rho mu sigma. And then finally, I just need to pass it through the gamma sigma. And when I do that, I end up with 3 factors of these, the metric tensor and 2 gamma matrices. And then finally, the string of 4 gamma matrices with gamma mu on the far right. Okay? So for this term, I can use the cyclic property, right, and move it to the front. Right? And that's going to be equal to the same thing I have on the left-hand side. So just add this to both sides and then divide by 2, right? And then use the identity that we have for the trace of 2 gamma matrices. It's 4 times the metric tensor, depending on their indices. And we get it something like this. So the trace of 4 gamma matrices is kind of linear superposition of the products of 2 metric tensors. Okay, we pair each of the indices together. Okay, so there's 3 different ways you can pair them together, and the one that couples the one that we group the first and the third together comes with a minus sign. Okay, so that's the trace of 4 gamma matrices. Right, and in this class, we'll the most we'll see is a trace of 4 gamma matrices. Okay, but in real life, a lot of times you'll run into cases where you have a string of 6 gamma matrices, and you have to take the trace. Okay, and like I said, there is. Yes.
The derived 6 gamma matrices, what we need to do, we need to move 1 gamma matrix to all others, and after that, do the same thing, but 6 times.
Yeah, exactly.
5 times instead of.
Yeah, exactly.
Okay.
Yeah, it just gets a little more tedious. There's a lot more terms, but it's the same idea. The general idea is that, like I said, no matter how many you have, I'm trying to think of the most that I've ever run into, but I can't remember if it's 8 or 10, but yeah, it's the same idea. Whatever you have, you just anti-commute the first one all the way to the end, and then you cycle it back to the front of the line. Okay, and that'll eventually get you what you need in your expression. Okay. All right. So I'm thinking about maybe assigning n equals 6 as a homework problem. Okay, I'm thinking about it. Okay. All right. So we know now how to do the traces that we need. Right. We said that from our matrix element squared, we're going to need the 2 case, right? And we're going to need the for case because remember in these slashes, there's some gamma matrices. But before we do that, we're going to run into cases where we have to take the trace of gamma matrices with gamma 5. Okay, so let me take a second to work out that case. Okay. So let's take a look at this. Okay. So since we know that gamma 5 can be constructed from the other 4 gamma matrices, so gamma 0, gamma 1, gamma 2, gamma 3, that means that this is it. There's an even number of gamma matrices here. So if I try to take the trace of gamma 5 with any number of odd gamma matrices, I'm obviously going to get 0, right? Okay, so that means that the trace of gamma 5 of any odd number of gamma matrices is going to be 0. Right? Okay, so let's start out with the simplest case. What about gamma 5 by itself? Okay. Well, here we can use a trick where we insert 1 in the form of gamma 0 squared. Right? And then I use the anti-commutation property of gamma 0 with gamma 5. Right? So that passes that through. Right? That gives me a minus sign. Okay? And then I want to use the cyclic property to pass this to the front. Okay? And then from there I can use gamma 0 squared is equal to 1. And so I find again that the trace of gamma 5 is equal to negative the trace of gamma 5. And the only way that can happen is that the trace of gamma 5 is 0. Okay. Okay. It turns out that the same trick works.
Excuse me?
Yeah.
How did you go from line 1 to 2 to line 3? Oh, just permutation, yeah.
Yeah. Yeah, it's just, it's cyclic permutation. Okay. So it turns out that you can use the same trick to do the calculation of a trace of gamma 5 with 2 gamma matrices. There you have to insert 2 factors of some gamma alpha, where you have to enforce that alpha can't be equal to mu or nu. Right? But you can show that by doing that and using the cyclic, using anti-commutation relations and the cyclic property, you can show that this thing, the trace of gamma 5 with 2 gamma matrices, is also 0. Okay, it also vanishes. That's another potential homework problem. Okay. All right. So what we find is that the first non-vanishing trace term of gamma 5 with gamma matrices is gamma 5 with 4 gamma matrices. Okay. And so this does show up from time to time in certain calculations, and actually it's kind of infamous. I'll tell you a story in just a minute once we do this. Okay. So in this case, what was I going to say? The trick still works. Okay, but it only works if all of the gamma matrices appear. What do I mean by that? I mean that this thing is going to be non-zero if and only if, it's going to be non-zero if mu, nu, rho, sigma equal 0, 1, 2, or 3, or some cyclic permutation of that. Okay, so you can show it, just by.
And it has to be a cyclic commutation. It can't be.
Well, yeah. Right. That's what I was going to say next, right? And you could do it with 0, 1, 2, 3, right? And then you could say flip 0 and 2 and do the same calculation, and what you find is you get a minus sign, right? So you find that it's only positive for cyclic permutations, right? And so that's telling us that this trace of gamma 5 with 4 gamma matrices has to be proportional to our good old friend, the 4-dimensional Levi-Civita tensor. Okay. All right. And in the usual Peskin way, you can show by plugging in 0, 1, 2, and 3 explicitly, and that it's easy to show that the overall constant is minus 4i. Right? So here we said that it's proportional Levi-Civita tensor, and you could show by just explicit plugging in that you get minus 4i. Okay. Okay. So my story is that when I first started out, there was a famous experiment at Brookhaven that was measuring the dipole, the electric dipole moment of the muon, right? And this was an important measurement because new physics can make contributions to virtual corrections, to on the theoretical side, and they did the measurement.
Magnetic dipole?
Yeah, magnetic dipole. What did I say? Did I say electric? Yeah, magnetic dipole. Yeah. And so they did the measurement. They compared it to the results, the theoretical results, and they saw that there was a small discrepancy. Right. And this was huge news, and people were going around saying, "Oh, this is the first signs of supersymmetry," and all this stuff because Susie would give you, the right amount of deviation from that number. But it turns out that the person that did the calculation, there was some issue with this because the calculation depended on, there should be a gamma 5 here.
Yeah, so thinking good about that, but I didn't want to interrupt your story.
Yeah. So it ended up that the person who did the calculation was using a piece of code that I've used as well. It's called Form, that has some weird convention that has to do with this factor of 4 and this factor of I. Okay, and so when they went back and fixed that, the result agreed exactly with standard model results. So that's an instance where you have to be careful, when you're doing these things. Okay, and like I said, I had to deal with this a lot because my thesis was on production of the pseudoscalar pittings, right? And a pseudoscalar, has gamma 5 in it, right? So I had to do a lot of these traces with gamma 5. So I had to deal with this issue of putting in this, factor of I don't remember what the code gives, but yeah. So it's an instance where the theory people were wrong. Okay, so theorists can be wrong. Every once in every decade.
You don't say.
Okay. So since the Levi-Civita tensor pops up, I thought I would write down some useful identities involving it. So this is the case where you're contracting all the indices, you get negative 24. Here's a case where you're contracting 2 of the indices, you get this Kronecker delta function, and if you're, let's see, this is 2. Oh, this is where I'm contracting 3, sorry. And here's where I'm contracting 2. Okay. So those might come in handy if you have, if you're computing, a matrix element has gamma 5 in it, right? And then you have to take modulus squared. Okay. That's where these things would come in, okay, to get the matrix element squared. Okay, and finally, another useful identity that you can put to use sometimes is that of these gamma matrices, you take a trace of these gamma matrices, you can actually reverse the order. All right, so that has nothing to do with the cyclic permutation or anything like that. You can reverse the order of the gamma matrices inside the trace. Okay, and I don't want to spend time on the proof that involves using the charge conjugation operator and some other stuff, but Feskin has the proof of it. Okay, so these are just little things like this. Sometimes can save you some computational time or time banging your head against the wall trying to figure out why the trace is not working out or whatever. Okay. So sometimes you'll also run into cases where a lot of times, like in loop calculations, you run into cases where you have a trace with a string of gamma matrices, and in that string of gamma matrices, there's 2 that are being contracted, right? So one that has like gamma mu up and one that has gamma mu down, okay? And say they're separated from each other by a string of gamma matrices. Okay? So a lot of times it's easiest to just go ahead and contract those guys before you take the trace. Okay? Because what it does is it reduces the number of gamma matrices that you're taking the trace over. Okay? And so what you have to do is you have to you move one of the gamma matrices to the other one by using the anti-commutation relation. And then when they get next to each other, you can use the identity that gamma mu, you can raise both of these guys, right? So by inserting a metric tensor. And then you use the fact that this thing is symmetric, so you can symmetrize it by using an anti-commutator. And then the anti-commutator just gives you another metric tensor, right? And when you contract 2 metric tensors, you get 4. Okay, so gamma mu, when you contract the 2, gives you 4. Okay? Okay. So that's the case that they were right next to each other. So here's a case this lecture is loaded with possible homework problems. Okay, so here's some other identities where you have a case where gamma mu up and gamma mu down are in the same string, and you want to contract them. Okay, so here's a case where you have 1 gamma matrix between the 2. Here's a case where you have 2, and finally 3. Okay? Like I said, if you have to prove these, I mean, the thing to do is just take gamma mu here and then move it systematically through these, other gamma matrices and then contract it. Okay, and what you should have is something that looks like this on the right-hand side. Okay. Any questions on that stuff? It's all the technology part that we're going to need.
And you understand this, you symmetrize those gamma mu, why we are allowed to.
Because they're all the mu and the nu are being contracted.
Yeah. Right.
So you can say that. Because G mu nu is symmetric, right? So you have gamma mu. Right, so I can write this. I can because these are dummy indices, right? So I can change these to nu, this nu, and this to mu, right? Okay. All right. So let's get back to our cross section. Okay. So remember, this is what we're trying to compute, right? We need to compute this thing, the matrix element squared, and then once we have that, we can plug it into one of our formula for the cross section that we worked out a couple weeks ago. Okay? So let's do it. Okay. So here we have our trace. Okay, and we've got all the technology now that we need to do these traces. Okay. So I'll work out one of these, and I'll let you convince yourself that the other one works out basically the same way. Okay. All right. So I'm going to consider the first trace. Okay. So the first thing I'm going to do is just square everything out. Okay. So I get the 4 gamma matrix term, the 2 gamma matrix term, and then these cross terms give me 3 gamma matrices terms, right? And so automatically I can toss those out, right? So you can say, okay, so this P / gamma mu gamma nu, I can pull out the P 4 vector, and these should be gamma matrices. Gamma matrices, right? And the 3 gamma matrices, you take the trace, gives you 0. Okay, so automatically you can drop those cross terms. So what we have left is the trace of the 4 gamma matrices, where I pulled off the 2 momenta, and the trace of 2 gamma matrices. And here's where we can just go to our table of the stuff that we've just worked out. Okay? So I plug in the expression for the trace of 4 gamma matrices. It's right here, and then the identity or the relation for the trace of 2 gamma matrices, right, is this term. Okay? And then I can start to combine everything. So what I do is I pull in, now that I have these metric tensors, I can pull these factors of momenta in, And what it's going to give me are either dot products like this, p dot p prime, or combinations of 4 vectors. So p prime u and p nu. And finally, I can just combine everything to get an expression that looks like this. Okay. So it's just once you square everything out, user identities for the traces is all basically algebra at that point. Okay. Right? Okay, so that's the trace of the electron line, right? The trace of the muon line works out and it gives you an identical result. Okay, except you exchange p's and p's with k's and p primes with k primes, and obviously the mass. Okay. All right, so we've got the 2 traces, and now what we have to do is put it all together. Because so I just showed you how to do this, and then I gave you the expression for this. So we just got to multiply those 2 together and see what we get. All right, so it's a mess. Okay, and so I squared it out, and then I read in Peskin. I couldn't figure out why my expression, because I had all these electron masses in there, and he didn't have any. I couldn't figure it out for a while, and then I actually read what he wrote. He said, I'm going to set the electron mass to 0. So that was a waste of 20 minutes. Because I thought, oh, there's some symmetry or something, and the electron mass is canceling out. That wasn't the case. Anyway, so you square it out, and I dropped all the electron mass terms. And what you see is there's some cancellations between these, like this term canceling off these terms, right? And some other stuff. But you can combine them, right? And what you end up with is something that looks like this. Okay, nice and neat, nice little, dot products between our 4 vectors, and that's it, right? So we've got a nice compact scalar expression in terms of external momentum and our mass, right, and then our momentum exchange. Okay. And what we need to do now is we need to specify what our momentum vectors are. Okay. And to do that, we have to specialize to a particular frame of reference. Okay. And then once we have that, it's like it's like kinematics from physics 1, from freshman physics. Okay. You just have to set up the collision diagram and stuff. Okay. But what this is going to allow us to do is going to allow us to express this thing in terms of kinematic variables like energies or angles, or we'll see later on that you can express them in terms of invariance, called the Mandelstein invariance. All right, so we're theorists, okay, and so we'll take the simplest way out, and that is to work in the center mass frame. Okay, so you can work this out in a lab frame. You can work it out in whatever frame you want. Okay, or you can work it out in one frame and boost everything. Okay? And it's a good exercise to know how to do that, because that's the real world, right? So at hadron colliders, you're never in the center of mass frame, because those quarks and gluons, the things that actually collide, are not moving at the same energies, right? The same speeds. Okay, so there's always you compute things in the center mass frame, and then you have to boost it into the lab frame. Okay. So this is our picture of what's happening. Okay, so I've got my 2 electrons, right, and they're massless. So their 4 vectors are really simple, right? And I've set it up so that the beam is on the z-axis. Okay, and these guys collide, right, and produce my 2 muons that come out back to back. They have to because of conservation of momentum, right? And I'm just using simple kinematics here, so here my K and K prime, my final state 4 vectors look like this, right? And this guy has to have the same magnitude as that guy, so that's why there's no prime here. And the magnitude of this guy is just E squared minus the mass of muon squared. And since we've set up everything on the z-axis, the k dot z is just going to be magnitude k times cosine theta. Okay? So what we need, we need to, in order to compute the matrix element squared, we've got a few things that we have to compute, right? A few dot products, basically. All right, so q squared is p plus p prime. So in this case, p plus p prime, the 3-vector piece cancels out. So that's just 2 times the energy squared, you get 4e squared, right? P dot p prime, same thing, give you e squared plus e squared, gives you 2e squared. And then, you got the p and the k, or p prime and the k prime, you get some factor of cosine theta, and if you got p into k prime, or p prime into k, you get the opposite sign, okay? So those are the 4 dot products that you need, okay? And so what we want to do is plug those back into this expression that we had. And so we're going to do that. We get something that looks like this. Okay. So I have I've replaced the q squared here. Okay. Here's the first term, and it turns out that it's the minus sign squared. The second term gives me the plus sign squared, and then I have my muon mass term. Okay. And so what I see is when I square it out, these cross terms are going to cancel. Okay. So the cross terms cancel. Okay, and then I can factor out some e squareds here and there. Okay, and I get down to here. Okay, now I've got k, the magnitude of k squared, so I'm going to replace that with the energy squared minus mu squared, the mass of muon squared. Okay. And then finally, I can factor out one more factor of e squared to cancel this guy off. So I get something that goes like the coupling to the 4th. Plus these terms, 1 plus this muon squared over e squared, and then a term that goes like cosine theta squared, okay? With the prefactor that looks like that, okay? So that's about that's as far as you can take it, okay? We've got everything now in terms of the energy of the particles, which we control, right? Those are the energies of the incoming electron and positron, and the scattering angle. Okay. So now what we need to do is turn this matrix element squared into an observable. And the observable that we want to look at is the cross-section, or the differential cross-section. Okay, so a couple weeks ago we worked out this formula. This is for the specific case where you have 2 particles in the final state, right? So the EA and EB here, so this is the general expression. The EA and EB are the energy of the incoming particles. Okay, VA and VB are the velocities, or the speeds of the particles incoming, and those we take to be, they're close enough to the speed of light that we can just take them to be the speed of light. Okay, and magnitude of P1 here, this is the magnitude of one of the final state 3 vectors. This is center of mass energy, and then finally our m squared. So for m squared here, we would plug in this box. So including 4. Okay. All right, so for us, do a little translation. So EA and EB, we want to express in terms of the center of mass energy. It's just the center of mass energy divided by 2. Right. And the magnitude of P1 for us is magnitude of K, which we've already worked out. And like I said, VA minus VB, it's in units of speed of light, so it's a factor of 2. Okay, because one's going this way, one's going that way. Okay. All right, so I plug everything in, right, and I've snuck in. Here I had e to the 4th, so I'm replacing e to the 4th with a alpha squared term. Okay, so there's a factor of 4 pi squared that's coming in with it. Okay, so that cancels off some stuff. Yeah. There's a factor of 2 pi squared here. So we end up with alpha squared. So it's going like alpha squared. and it's going like 1 over energy squared, and then everything else is dimensionless, okay? That's important because this thing, we want it to go like 1 over E squared, right? Because in our natural units, 1 over E squared is units of area, okay? So this is a cross section, should have units of area, and it does, okay, in our natural units. All right, so finally, I can do this integration, and I think even I can do this integration by hand. Right? And you end up, once you integrate over the solid angle, you get the total cross section. Okay? And again, we see that it goes like 1 over E squared. So we'll be interested in, a lot of times, the high energy limit, so where the energies, the colliding energies are much greater than any of the masses that are considered, or that are in the process. And so that's what I've done here, is I've taken the limit where E is much larger than the mass of the muon, and so we see that the differential cross-section goes like 1 plus cosine squared, and the total cross-section, the leading term, goes like this 4 pi over 3. Okay? Okay, so that's it. That's our result for E plus E minus goes to mu plus mu minus. Okay, and what we would want to do now is take our calculation and show it to our experimental friends and say, go run this experiment and see if it agrees with our theory. Okay. The first thing you'd want to do is make sure that the calculation, or your prediction compared to experiment matches at threshold. In other words, so if the cross section is 0 up until you hit the energy equals twice the mass of the muon, right? It's in our mass energy, and then you can start producing muons. Okay, so that's what we call threshold. Okay. And so what you would do is at threshold, so QED has a prediction. There's some energy dependence that comes in from the matrix element squared we've seen, right? So these types of corrections here, and then there's pieces of the calculation that just come from phase space. Okay, and so this is a comparison of just above threshold the QED prediction, right? So these are the corrections coming from the actual scattering, compared to just a pure phase space. So that would be like if your cross section was just a constant, didn't have any energy dependence. Okay? So in the early days of QED, this was an important test, because you want to make sure that you're not just getting a pure phase space type effect. Okay? And then finally, so what we did was, we did it for the case of muons, right? You can do the same thing for taus, for tau leptons, okay? And this is from 1978, okay? So it's old, right? But it shows you, so this is it's a ratio of taus to mu's, okay? So it's a ratio of the cross section, so it's like right here, right? And the reason they take ratios a lot of times when they're doing these measurements is that a lot of uncertainties will cancel out. A lot of, not uncertainties, but like systematic errors and stuff like that. So a lot of times you'll see things presented as ratios, okay? Because, like I said, a lot of the statistical uncertainties and even statistical ones will cancel out. Okay, so this is a comparison between. So the solid line is the prediction from theory, QED, right? And then obviously these points are the data. Okay, you see that there's a really good agreement between what we would have calculated. So this is directly from this guy, or maybe from our exact expression. But the important point is that the data is, that the experimentalists are doing their job right. Okay? I'm just joking. But yeah, so there's a good agreement between QED and expressions. And I'm sure that more modern, this has probably been tested, over and over again, like say at the LEP collider back in the 90s, early 2000s. I'm sure there's a better plot of this where the error bars are much smaller.
The solid line is a prediction? Or
Yeah, that's a theoretical prediction. I think it's just tree level. I don't even think it's.
It's not feeding the data.
Well,
it is.
I would say it is.
I mean, not perfectly, but again, you only have a few.
And this is, like I said,
Data
this is back
points.
in 1978, right? So this is almost 40 years old. So the technology, that's what I'm saying. If you go and you look and see what LEP did, LEP collider back in the early 2000s, the error bars are probably minuscule. And I didn't hear anything about QED being wrong, so I'm guessing that it fits. Okay. This is some anomaly here. This is some statistical fluctuation, I'm sure.
I mean, so we have the prediction, and we have the plot that there is data on it, and we can fit the data and get a line that is.
Yeah, you could. Yeah. I mean,
I was wondering if it's just fitting the data that solid line.
No.
It's just
This is the prediction.
Okay.
This is the prediction as a function of center mass energy. Okay. So what it is it's basically so this is the total cross section, right? So if you look at the high energy limit, I don't know if this was at. But what it is, it's basically a ratio of the tau term to this term, right?
The energy is on the x-axis.
Yeah, center mass energy. Right, so they dial up the center mass energy until they hit the threshold for 2 muons, which is about 3.5 GeV, because the muon mass is about 1.7. Okay. So at the end, just summarize what we did. So we pick a process, we draw the diagrams for whatever the process we want. We use the Feynman rules to write down the amplitude. Take that amplitude, we square it, and average or sum over the spins. When you look at this list, it looks a lot simpler than what it is, but this is kind of the recipe. Okay, so you take the matrix element, you compute the complex conjugate, you sandwich those together, and then you can replace things like UU bars, right? With when you sum or average, you can replace those with P/ plus or minus M's, right? And then you have to take the trace over those things. But now we've worked through all the stuff that you need to take those traces, and so you can do that, and then plug it into a cross-section formula, and that's it. That's the end of the day. And then you go off and you compare to experimental stuff. Okay. So that's the end of today. And what we'll do next time is we'll talk about some other processes, and we'll see that, like I've said, there's some symmetries that you can invoke in order to, once you compute one process, you can invoke some symmetry to compute a different process. You don't have to go through this whole thing again. Okay. All right. Any questions? So if you have questions that you come up with later, just email me. Okay. All right, but I encourage you to, if you're interested, encourage you to work through this because it's a nice exercise. I mean,
Getting terrains.
Hmm?
And exercise of getting terrains on the element.
Yeah. What do you mean?
You said anchoring.
Oh, the homework? Yeah, I might give you some homework on proving some of those identities. But what I'm talking about is go through this process, right? For E plus E minus goes to B plus B minus, right? Because it's it is And, you know, just use those identities that we worked with for the gamma matrices. All right, I'll see you Wednesday.
Yeah, okay, thank you.
See you.
Goodbye.
Bye.
Okay, maybe for some probably issues we can also ignore them as something
Yeah. Yeah, yeah, that's it, yeah, in fact, I mean, that's what they would have done at Web, I mean, at Web, they were at 200 something dB.
Thank you.
Okay, I'll see you.